Okay, a little bit of change of pace here. We're going to move from talking about pure persistent memory to talking about persistent memory over fabrics, PMoF. Let's see if I get the, there we go. I'm going to jump ahead a little bit and set the context for this session before we go back to the agenda, but we're really focusing here on persistent memory as a target of memory operations. First of all, I think that's been made pretty clear this morning. We'll kind of emphasize that as we go on. This is about memory, not about storage. And it's about persistent memory accessed over a fabric or a network. So that's kind of the scope of where we're going to be in the next 20 minutes or hour or so. Agenda-wise, I'm going to start out talking a little bit about persistent memory over fabrics as viewed by the consumer and try to give some guidance to the fabric community as to what would be desirable features of a fabric that would support persistent memory. After that, Stephen Bates is going to come up and talk a little bit about the implications of building a remote device, a target device, what kind of considerations there might be there. And finally, Rob Davis from Mellanox is going to finish up by talking about some of the work that's going on in some fabric development areas, some specific fabrics there. So the consumer's view, maybe a little bit of guidance to the fabric community. I do work for Cray. That's my day job. I'm also the Open Fabrics Alliance Vice Chair, as well as the co-chair of the Open Fabrics Interfaces Working Group, which is focused on APIs for fabric kind of applications. So I'm kind of in a cat's bird seat there. So what the consumer would like to see, we've talked a little bit about this morning. You'd like to see persistent memory looking just like memory, not like some version of faster storage. And I want to extend that idea a little bit further and say not only is it looking like memory, but even if it is over a fabric, it should still look like memory. That would be the ideal goal here. So we want to be able to treat it like memory as much as possible, but we also want to be able to take advantage of the fact that it has persistence characteristics. And because of the fact that it's over a fabric, which introduces some asynchronicity, there are some implications associated with that I will touch on. So who are these consumers? And I'm not talking about guys sitting at home watching their TVs. A consumer here is someone who consumes network services. That's the context of the word consumer, the way I use it here. And how are they going to use this new technology? So let me give you kind of three high-level use cases for the application of persistent memory. This is the one that I think sort of launched the whole thing and the one I think most people are most familiar with when they think about persistent memory over a fabric. It's this idea of high availability, including replication. So the basic idea here is that whatever data is written in local persistent memory is replicated over a fabric to remote persistent memory. This is, of the three use cases I'm going to describe, this is the one that's most likely to lend itself to kind of block kind of operations. But in general, I want to kind of discourage this thinking about, remote persistent memory as just a fast block device. Kind of the way it works, there's a user over there who's doing a bunch of store operations. Ultimately, he does a commit, and then there's a library below that that forces a flush across the wire that forces that data to be flushed to remote persistent memory, local persistent memory, and to remote persistent memory. Then eventually, there's a completion that comes back that says that that data has in fact been made persistent remotely. This one I think is relatively familiar to a lot of people. Second use case, remote persistent memory. This is where it looks like just a giant pool of memory that's available out there for the use of the consumer. In this case, we're talking about expansion of on-node memory capacity, taking advantage of persistence or not. So there are use cases where you can imagine what you really want is just a giant memory service out there on the fabric. It doesn't necessarily need to be persistent, but the persistence characteristic is there if the use case takes advantage of it. This is sort of the extension of this idea of disaggregation of servers that we've been talking about for years. I think Jim mentioned it earlier this morning, this idea of a storageless server. Well, what if you had a memoryless server as well? Kind of where we're going with this long term, this notion of disaggregation of memory for compute. The way it works, I've shown an operation here, a put, which is distinguished from a load or a get, and that a load or a get is a CPU-specific instruction. Think of the put as the fabric version of a load or a store operation. Well, the put being the load and the get being the store. And then a completion that comes back. I've shown here two different applications that are both sharing some resource from that persistent memory service that's available on the left-hand side. There's no interaction between them. I just tried to show that there's a system-wide service that's made available to consumers that want to use it. The third one, shared persistent memory. In this case, there is some interaction between the applications that are sharing this persistent memory. So this is, again, this notion of a shared, remote shared memory service that's out there on the fabric somewhere. And in this case, I've shown this notice operation here. Is there, well, that wasn't a good idea. There we go. That's not a good idea either. How do I get back to where I was? Jenny? Never mind, I can figure it out.
Sorry, I was out of the room. Where do you want to be?
Right there. There we go. That's what happens when you give an engineer a pointer with too many buttons on it. I was hoping there was a laser pointer. What's that? Ah, hey, here we go. All right. So avoid those bottom two buttons. All right. The idea here is that one of the consumers is doing a put operation of some sort, and there may be some sort of a notice or subscription that goes out that notifies other cooperating applications that there's been an update or a change made to whatever the shared data happens to be that allows him to go off and do a get if he wants to do so. Think of this as a distributed database kind of an application. I think that's probably the easiest one to kind of get our heads around. Let's see, persistence can be used to guard against node failure. Okay, that makes sense. All right, so those are the three use cases. Again, replication, remote memory, and shared remote memory. So the objective for us as Fabric developers, I'm a Fabric guy, we would like to present this persistent memory to the consumer as much like local memory as practicable. Let's make it look as much like local memory as we can. But there's this little issue of physics that we kind of can't get around. So there are certain things that we're going to have to do, like it or not, and we'll work our way around those. So what does that actually mean from a Fabric perspective? Think about for a minute the difference between a memory operation and an I/O operation. You can kind of characterize them. I think we kind of understand this pretty well at this point. But in the case of a memory operation, you're talking about a load or restore, movement of data from a CPU register into memory. It's sort of fundamentally different from the basic idea of a storage operation where there's an extent of data that's moved from memory to a storage device of some sort. Let's not think about it that way. Let's think about this more as a memory type operation. The other thing to keep in mind is that I/O tends to be asynchronous, which is a function of the fact that storage devices historically are pretty slow relative to CPU speeds, and fabrics only make the problem worse. Memory operations, on the other hand, tend to be synchronous. This is the one area where we're going to have to make some compromise, I think, from the perspective of the consumer to account for the fact that this persistent memory is remote. We're going to have to deal with the fact that those operations are going to have to be asynchronous going forward. So what do we have to do? Streamline the API. There was some talk about that this morning to make it look more like memory operations. We have RDMA style operations, yes, but there are opportunities there to improve the API itself, the way that we do these operations over the wire. So I think we can actually streamline the API, make things go faster, and make it look more and more like memory and less like, posted operations. We have to manage asynchronicity. I already mentioned that just a second ago. It's a necessary evil. We can't get away from that. Explicit control over when persistence occurs is part of it. The other part of it is the notification about when persistence has been achieved. So we got to do those two things, and they have to be fabric features. They can't really be a consumer or an end node kind of a function. It's got to be on the fabric itself. And we want to make it fast. So are there opportunities, for example, to emphasize wire efficiency? I was really fascinated by the keynote this morning when he mentioned opportunities for stepping outside of, let's say, standard Ethernet protocols. Are there things that we can do in certain constrained environments to improve the wire efficiency, reducing overheads and things like that? I guess the key here is that as memory speeds become faster and faster and approach DRAM speeds, persistent memory speeds, the fabric becomes more and more of an issue, and we're going to wind up having to deal with the actual physics on the wire itself to the extent that we can. And when I say physics, I don't mean changing the speed of light. I mean reducing headers, making things more efficient like that. Streamlined APIs. This was mentioned this morning. I think there was a really good discussion about this, storage versus memory. So I won't harbor in this too long, but I think the thing that's concerned me about this, and I'm heartened by the things that I've heard this morning, is if you start thinking of this in terms of just remote storage, what you're going to wind up with is faster storage. And faster storage is a good thing, but that's not what we're after here. We're after remote memory operations. So even if the data at the far end is mapped as a memory map file or some mechanism like that, think about keeping our heads the idea that we're trying to do memory operations, not storage operations. So to highlight that, I've kind of shown, there's load store type operations over here, or memory copies that, as I suggested before, get reflected across the wire as puts or gets. And those are in sort of stark contrast to what you see at a standard POSIX interface. Okay, managing asynchronicity, what does this mean? Storage operations, typically the storage protocol has a synchronization point built into the protocol itself. Think about classic SCSI, for example, where you do a write operation or a write request, and then the target device does a bunch of stuff, makes the transfer occur, and then synchronizes by sending an ending status. It used to be called SCSI ending status. I'm not sure what the equivalent NVMe version is, but something like that. And that creates a synchronization point. And that's a function of the higher level protocol. The storage protocol itself is doing that. The consumer, being the storage client itself, is doing this synchronization. Such a thing is not going to happen in the case of remote persistent memory. So we're going to have to accommodate that somehow by putting the synchronization point in the fabric protocol itself. So somehow or other, there's a write operation that's going to occur across the wire, a memory request of some sort, and that's going to have to result in a completion that comes back that says that the data has been made persistent. What does that look like in a little bit more detail? Here's sort of four possible completions you might imagine. This thing that I've labeled AC, which means nothing. It just means that for that kind of operation, you want an acknowledgement back as soon as the local buffer is available for reuse. That's normally available today. This is what almost every fabric in the world does today, AC. When you get an acknowledge back over the wire, what it says is that the NIC on the far side has received the data. It really tells you nothing more than that. It just says it's been received at the remote end and in reasonable shape. AC is a little bit more sophisticated version than that. What that says is not only has it been received, but I've done something with it. So you can count on the fact that if someone else accesses that data, for example, it will be available when they want it. The one I'm talking about here that we need to talk about adding to the fabric protocols is this thing ACD, where we're actually reflecting an acknowledgement that says not only was the data received, but it's actually in the persistence domain. So you want to notify the client that, in fact, his data has now been made persistent. This is what I mean by we have to manage asynchronicity. So really two parts to it. One is the request has to indicate that this data is to be made persistent, and that could be done either by the way that the memory mapping occurs. So if you're writing to a particular memory region, for example, it's considered persistent, or you could consider adding an operation on the wire that says write persist, or maybe there's a flag to an existing wire operation that says do a write and make it persistent. And then there need to be completion acknowledgments that come back that say persistence has been achieved. So I'm getting to the end here, which is good because Stephen's chomping at the bit, I'm sure. What do we need to do? We need to enhance the API, so I talked about that just a second ago. We need to expose the fact that the persistent memory device is out there and that it has persistence characteristics, so the client knows that he's working with a persistent device. That could happen at job launch time. That could happen in a number of different ways, but somehow or other the client needs to know that the device he's working with is persistent. There needs to be some memory registration such that he knows that that particular region with which he's working is persistent. You can imagine a remote memory service where part of it is persistent, part of it is not. We need to have get style semantics on the wire. which are sort of similar to today's InfiniBand RDMA read and RDMA write. But again, I'm looking for improvements in efficiency there. Can we make those things go faster than they do today with classic RDMA style verbs APIs? We need to be able to control the persistence. So again, be able to say whether this data is being presented as persistent data or not, and we need completion semantics to go with it. Faster wires, always, always, always. We just want faster wires for sure, because that's going to make this remote device look more and more like memory and less like a storage device. We're never going to get away from the need for asynchronicity, I don't think, but if we get into that 500 nanosecond to 1 microsecond region that was mentioned earlier today, we're starting to talk order of magnitude where it begins to look like it can be treated as memory, not storage. Small message performance, we should be focusing on that. Again, this is not about block I/O, it's about byte level reads and writes. Of course, the byte level read and write is nothing but the diminishing case of a block I/O. A block operation that's 1 byte is a persistent memory byte level read or write. And synchronization in hardware, that needs to happen in hardware. The interesting one here to me, and this was hinted at again this morning, is this one here. Notice I didn't label this. I should have. In an earlier version of the slides, I had it labeled. This could be PCIe, or it could be a memory bus, or it could be something else. We shouldn't limit our thinking to say, you know, we're limited to PCI-style devices. It could be, the persistent memory could be attached to what I'm calling the provider here, which is really just a combination of the NIC in a hardware kind of fashion. Notice that I've shown this persistent memory server off to the side, so there's no notion here of software on the target side path at all. We're talking strictly about data that's taken off the wire and placed directly into memory by the hardware, by the NIC. I guess the picture is a little bit misleading in the way I've drawn it, but you can see where I'm going with this. More sophisticated access mechanisms, so keys and tagging, sort of things that are common in high-performance networks. We need to apply those to persistent memory to best effect to make sure that we can avoid any kind of software along the way. More capable NICs, so a lot of this stuff is going to wind up in hardware, not in software, and improved wire protocols that kind of go hand in hand with that. If you want to be able to place data directly into memory, there may be enhancements required to the wire protocol to support that. Okay, better APIs. They should match the lingua franca of the application, so the application shouldn't have to think in different terms. It should be able to just do a put or a get, and it should just plain work all the way through the wire straight to the persistent memory. No posting, no queue manipulation, just a put operation. That's the kind of semantic that I think we're shooting at. We should incorporate the semantics to control persistence. I've harped on that already. Faster wires, small messages at high transaction rate. They look more and more like memory operations, so keep those in mind when you think about fabric design. Think about small message operations, very high transaction rate. And think about building clever target devices that eliminate layers at the target, so no software along the way. The objective here, make references to remote memory as fast as possible, neglecting the speed of light and practical considerations. We'll leave those aside. Okay, that's my part. Stephen, I think you're up.
I started my timer. I better turn over the mic. Thank you, Paul.
For you?
Thank you. Is this working? Can everyone hear me? La la la. No. I only sing about block devices. I don't sing about persistent memory. So Paul gave us a very nice kind of background in terms of where, from an abstract point of view, are we trying to go. I want to get a little more specific, and I'm going to dig into a little bit more on the specifics of what we can do around persistent memory over fabrics today, and what some of the gaps are, and then hopefully Rob will finish off by talking about how we fill in some of these gaps to get us to a point where we can start working with real persistent memory over fabric systems today, and then start working on how we evolve them towards something that we can do tomorrow. So a quick reminder, this is actually from 2017, so this is a slide I did last year, and this really for me summarizes what I think make up the attributes of persistent memory. So 3 components: low latency. We've had a lot of discussion around latency. Zonomir gave a great keynote this morning, giving us even some quantitative numbers around what low latency really means. Memory semantic, we're not talking block. Paul was very clear on that. I totally agree. And then storage features, and the minimal storage features for me is persistence, right? So, without persistence, you can't store, but there's other storage features around things like data protection, so duplication or RAID, high availability, can I get at my data even if failure domains fail, and other kind of things around reliability, availability, and security, right? These are other storage features. So what I did is I used my Apple Pencil, which I love, thank you, Jim, for persistent memory over fabrics. And I basically updated this slide as a markup. And so the three functions stay the same, but we get this new requirement that we want to do this over a fabric. So we still need the low latency, we still want memory semantics, we still want the storage features, but now we need to do this at scale, over a fabric, managing all of the issues that are associated with that. So, the Holy Grail. Rather than looking at where we are today, let's look at where we want to be. So, Monty Python, I'm original. My dad was English. I grew up watching him laugh his head off to Monty Python, going, what the hell is he laughing at? Anyway, so the Holy Grail, in the movie, they had the knights that say ni. We have the knights that say si. The speed of light, right? So fundamentally, at the end of the day, there's certain things we cannot get around. Even SNIA can't standardize the speed of light, right? Or can we? I don't know. I don't think we can. So there's only so much distance that we can cover in a certain amount of time. And that puts a fundamental limit on how far can we go if, like Zonomir says, the hard limit is a microsecond. Right? That's 300 meters at the speed of light. But of course, we can't go at the speed of light. I mean, if you're traveling in a vacuum, you can. But if you're in an optic fiber, you travel at some fraction. There's a protocol on top of that, blah, blah, blah. So that kind of tells me, all right, there's certain ranges in which I can cover, assuming I have a fixed limit. But in terms of what it is we actually want to try and do, this is a very similar kind of message to what Paul was saying. The ultimate objective is to have CPUs that can do loads and stores, and this is x86 specific. I think this is a move instruction. Anyone who knows their x86 assembler can correct me. And these guys are doing load and store instructions, and they're affecting the bits that live on a persistent media that is somewhere else in the system over a fabric, right? And there could be many, many of these clients. And these clients don't all have to be central processing units. I actually would have updated this to say some of them can be more heterogeneous types of compute element, right? They could be graphic processors. It could be deep neural network training ASICs. It could be FPGAs. It could be whatever. And this is very like Zonomir's memory-centric model in the sense that we have all these processing elements that are basically addressing memory that just happens to be persistent. And they're doing it across a fabric. And they may be talking to multiple targets at the same time. They may be doing duplication. They may be doing erasure coding. They may be doing other things. So this is the goal that we want to get to. This is a hard barrier, right? There's other barriers in terms of technology that doesn't exist today. But even if we get that technology, we still have the knights that say C, all right? Unless someone invents tachyon travel or some other kind of optic fiber. And this is the Holy Grail. This is, everybody happy and living the dream. So, I do want to talk about what we can do today, but before I do, I want to talk about some movies that are coming soon to a cinema near you. So this is the collective I call Open Gen C6, because they're all going to merge into one. We know that, it just hasn't happened yet. So we have Gen Z, a new fabric, coming sometime soon, offering optional coherency, NVMe support, scale. We have C6, the ARM Power Strikes Back. Right? Come on. Right? So, and we have OpenCAPI, the return of the big blue. Right? That one was a little bit hard. Now, we do have an elephant in the room, or should I say Death Star in this case, in the form of legacy CPU providers who may or may not choose to play in this space. And the reality is, because of the knights that say C, right? Because of the knights that say C, we kind of have to align with what the processors or the processor vendors provide us in terms of how this matures. So I don't know where this is going to end up. If I knew how this is going to shape up over the next few years, I would already be in my private jet flying around and doing whatever it is. Because this is going to have to take some time to shape up. So I'm not going to dwell too much on this, and some other people are going to talk a little more about the specifics of these different protocols later in the day. I'm going to talk about, well, what can I go and see today? What movie is available for me to go and work with today if I want to go and build a Fabrics target? An earlier version of this slide might have had a something inside logo here, but I thought that was a little bit, I thought that was a little bit too much, so we didn't do that. So if I decided to go and build a persistent memory over Fabric target today, so I'm going to talk mostly about the target for now, what would that look like? Well, I would probably have some kind of Fabric attached device, a network interface card, and there's a few choices around, but the RDMA compliant ones are the ones that are probably the easiest to go and buy. And I can go to Rob's company, Mellanox, or I can go to Broadcom, and I can go to Intel, and I can go to Cavium, and I can go buy a range of devices. This could be InfiniBand, this could be Ethernet, and then we're running an RDMA protocol on top of that. Okay? These devices are all today PCIe connected to the processor. There's a couple of OpenCAPI flavors coming, and there will be some Gen Z, and there will be some C6, right? But most of them are PCIe today. And they go into a central processing unit, and then I connect my NVDIMMs on the DDR channel. Now this is the target, okay? This is not the client. The target isn't actually looking to process this data. It's not looking to do analytics on it. It's just there to act as a storage head node, or persistent memory head node, I should say, before Paul hits me. Because we're not storing, we're looking at memory semantics. Houston, we have some problems with this design. Can we set SCE to aux, please? That's an in-joke for anyone who knows it. And what are the problems that we have as we delve into this design? Well, an obvious one is the Fabric interface. I mean, Zonomir did some really nice quantitative analysis on what is the latency associated with doing RDMA. And that was really, really good. We do require CPU utilization on the client. The client is not doing load stores when it invokes an RDMA verb. All right? It puts the data somewhere in its local memory, and then it calls a function call. And it is a user space function call, so at least we don't context switch. But it calls a function call that basically hits some registers over PCIe on the NIC on the local side that then sucks in that data from the memory and puts it somewhere else. And that's great for replication of memory, but it's not really the Holy Grail, as I showed you a couple of slides ago. The client is not doing load stores. It is challenging to scale. I mean, companies are scaling RDMA networks to up to big sizes. I think Microsoft Azure is an example of a company that's doing that. But they're putting an FPGA in every server to help them do that. So it's not easy, as much as Rob would like to say it's easy. It can be challenging to scale RDMA, and it's definitely not coherent. Right? We're not talking coherency here. We have to invoke coherency through software, and that's going to be a problem. One of my biggest problems with this particular way of doing a target is, why on earth is this CPU in the way? Why do I have to connect to the Fabric, connect my persistent memory to the Fabric through a processor, if that processor isn't actually working on the data? Now, if I'm doing like in-memory databases, if I'm doing local persistent memory, this is great. Like, don't get me wrong, this is totally great for persistent memory, just not great for persistent memory over Fabrics. I have to now go get a processor that has the right DDR bandwidth, that has the right PCIe, and assuming I want to hang a lot of NVDIMMs off, that's probably a lot of channels of DRAM, which typically implies there's a lot of processors in there, but I don't need those processors. So why am I paying for them? Not so good. Also, you tend to end up having to have very instruction set dependent and very platform dependent things going on. Data direct IO, what instruction set architecture is here, how do I flush the caches, pcommit, cflushOp, all that kind of stuff, right? So those are things that in a local system I do have to worry about, but why am I worrying about them on a remote system? The persistent memory, it's expensive. It's not hot swappable. Someone mentioned that earlier. Linux supports hot swap memory, but NVDIMMs are not hot pluggable physically. We have capacity and scale issues. I already said, how many DDR channels do I need? That's a challenge. And I got to make sure my motherboard supports things like ADR. So does my motherboard support a persistent region that's going to keep power up on the right parts of the motherboard when a flush comes in? So how do we get around that? Well, before I show you what I think is maybe a better solution in terms of what can be done today, I do want to take a quick segue into NVMe persistent memory regions. So persistent memory regions are a feature that is being standardized in NVMe. We haven't finalized that standardization yet, but there is an ecosystem that's starting to appear. And my very good friend, Dave Allen, who's on the marketing board of NVMe, gave a talk last week on Bright Talk. It's recorded. I suggest if you're interested, you go look at it. And this is one of his slides that he gave that talks a little about where we are with persistent memory regions. A persistent memory region is just a standard way of exposing a PCIe bar in a way that's aligned with the NVMe spec. So an NVMe device, if you have an NVMe SSD or any other device that's saying it's an NVMe device, can advertise a bar, and now it can say that that bar has persistent properties. So I can now expose a bar and register it as persistent in a way that the operating system in standard can understand. So in the same way that we have really good NVMe support for Linux and VMware, this component of NVMe will also get good OS support. So now I don't have to do a proprietary method of a PCIe device that wants to say it has a persistent bar. This is different to a block device. Right? A bar is not a DMA kind of access in terms of it doesn't suck data in. It's a flat register space. Typically, they're small and they're memory mapped, and you use them for control or data placement. There's nothing to stop you having big PMRs. So we have an NVMe device in our company that's very programmable, and we played around with PMRs. We can do a 6 exabyte PMR. 6 exabytes. Now, try booting up a server when you're advertising a 6 exabyte bar. And every BIOS we found so far didn't like that very much. But we can do that, and we can change BIOS, right? BIOS is just code, so we can change that. Now, of course, I need memory to back that up, and nobody's sold me a 6 exabyte memory chip yet, but if you have one out there and you have it handy, just let me know, and I'll put it in. There are other companies that have PMR-enabled devices. Toshiba did a press release on PMR-enabled drives that they're going to market with. Everspin have PMR capability. And there's other devices that aren't quite a PMR, but they're very similar. And one of them is from my former employer, Microsemi, and their NVRAM card is also able of doing that. So think of it as an NVDIMM on the PCIe bus. And that's a really stupid idea for directly talking to persistent memory in a compute. But for a persistent memory over fabrics target, it's actually not a bad idea at all. And I'm going to tell you why. So how would I deploy that in my system, in my persistent memory over fabrics target? Well, I'd keep things kind of the same. I would still have a PCIe connected RDMA NIC. That stays the same. I still have a processor. And I don't need this switch, assuming I have enough lanes here. But I'm going to put the switch in here for a reason, and I'll explain that in a minute. And then I have these NVMe drives that have this PMR feature. So you can go buy these from Toshiba, from us, from somebody else. And I think we're going to see more and more of these over time. So you don't have to buy them from any particular vendor. And there's a very, very good standard around it. It's NVMe. NVMe is a great standard, and a lot of people are working with NVMe. So Houston, we have less problems, fewer problems. What's gone away? Well, none of our fabrics problems have been solved by this. So I haven't solved any of the fabric problems, but I have solved quite a few of the other ones. Why is the CPU in the way? It isn't. I can now basically DMA directly to this PMR. Very similar to what Zonomir was showing in his work with his phase change card. I can memory map this PMR, it's a memory region, and I can DMA directly to that from the NIC. All right? No need for the processor to consume the data at all. It can still be in charge. It can still run Linux or your favorite operating system and manage everything and step in if something goes wrong, but it doesn't have to be the one in the way. So all my ISA problems go away. I no longer have to worry about CFlush and pcommit and whatever the ARM equivalent is and whatever the RISC-V equivalent is. I have nothing to flush. Nothing's in the CPU caches that's persistent. The persistent data is going here. Now, I do have to flush these, but the great thing is it's not an architecture-specific flush anymore. It's an NVMe-specific, PCIe-specific one. So not architecture dependent anymore, standardized. It's going to work no matter whether this is Intel, whether this is ARM, whether this is IBM Power, whether it's a RISC-V. The persistent memory, well, it's probably still expensive. I'm still using whatever type of memory technology is available. But the good thing is now I can plug it into 2.5-inch drives, U.2s. Those are hot pluggable. So I can now plug these in, take them out. In theory, they could fail. And assuming I have some kind of redundancy across them, it would work just like a RAID system does today. Capacity and scale issues, I think, are improved. I can go to Celestica, or I can go to WeWin, and I can buy a JBOF, which I can put like 60 or 80 or 120 of these into. And with PCIe switch fanouts, I can just make sure that I have enough PCIe throughput. And maybe I have multiple of these NICs. I don't have to have one. I could have many of them. I have no motherboard requirements whatsoever. All right. I got to be careful of PCIe ordering rules, but they are standardized, and anyone who has worked on PCIe switches can develop a system to make sure that those ordering rules work in your favor. I don't even care what PCIe speed this processor's at. If I have a Gen 4 switch, and I have Gen 4 capable NICs, and if I have Gen 3 or Gen 4 capable drives, I don't give a crap if this is Gen 3, or Gen 2, or Gen 1, or Gen 0. What's Gen 0? Right. So I've decoupled the target side CPU, PCIe, and DDR requirements from performance. They're just managing. And the firmware interface, also all these problems which are still here, I can upgrade this over time. This could maybe become a Gen Z to PCIe bridge, or an open copy to PCIe. And maybe this switch becomes a PCIe/Gen Z switch. And so this is Gen Z, this is Gen Z, and then this is still PCIe. And Gen Z is great support for NVMe. So that actually plays quite nicely. I haven't solved all my problems, but I got rid of a bunch of them. Switching over to the software. So the problem I have with the software is when I went and looked for software for persistent memory over fabrics, this is me, and basically there's nothing out there. For the sake of time, I'm not going to go through this slide in a lot of detail. The call to arms, for want of a better way of putting it, is that we do have an ecosystem that's maturing around the hardware to do persistent memory over fabrics. I think the big challenge that we have is on the software side. We have some really, really great software for locally connected persistent memory. The work that Amit and Microsoft were talking about, persistent memory-aware file systems, are really very, very exciting because they allow us to use persistent memory without massive changes to our applications and see really material benefits. But none of that is extended yet to work over fabrics. And so there is a bit of work going on. Christoph Hellwig at HDST is working on some extensions to NFS that may actually work, but the code isn't even ready yet. So we're still very, very, very nascent in terms of that. And without the software, the hardware is meaningless, right? So we have work to do. So I'll leave you with this thought and hand you over to Rob. It's the software stupid. I always like to put in a picture of my kids, so that's them. And this is pretty much what they tell me on a daily basis. Dad, it's the software stupid. Thank you very much. Oh.
I'm sure they say something stupid, but probably not software. Good morning. I'm going to try to put some reality around the discussion. These concepts that Paul and Stephen talked about, I'm going to try to show how you could actually try some of them today with existing technology. So the underlying technology for what I'm going to show is RDMA, or Remote Direct Memory Access. So I'm going to start out with a little bit of background on that. So what RDMA is the remote version of DMA. I'm sure most of you in the audience know what DMA is, and for those that don't, it's basically a small engine hardware in the processor that allows you to move memory from one part of the memory to the other without sitting in a software loop. So it's a hardware engine. And RDMA is just the remote version of that. It's direct, meaning there's no, there's no software involved, right? So it's totally, no kernel involvement. Everything is done by the adapter card. So instead of the engine that moves that data being in the processor, it's on the adapter card, the network adapter card. So there's an engine there that you give a pointer to some memory. You've got a pointer to some memory on the other side of the network, and it takes it from there. And it is a memory transfer, so we're not supposed to talk about storage here. So this is memory, even though I focus on storage at Mellanox. This is a memory transfer, and this is happening between memory on one machine to memory on the other machine across the network. So there's no buffering in the way. There's no TCP/IP stack with transfers. And from an access perspective, this can be done with blocks, or it can be done all the way down to bytes, as they said in the keynote earlier. So there's send, receive. These are the different capabilities of an RDMA adapter, and the ones we're going to focus on are read and write. So why? Well, as has been said also by many of the other speakers, it's about latency. RDMA is super low latency because there's no software in the way. It's all done by hardware. There's zero copy. The network stacks are bypassed. There's no operating system, as I said earlier. It's very reliable. So even though there's no network stack, that is in the RNIC. So it's transferred to hardware. So there are mechanisms that are making sure the data is sent across the network, is in order, has no errors in it. If something happens, recovers from it. But it's all in hardware, so it's super fast. And if there's no exceptions, if nothing happens, then it's really, really fast. And it's reliable. And you get to take advantage of the resiliency of the network. So InfiniBand networks have been around for almost 20 years. Ethernet networks for what? Probably 40 now. So there's a tremendous amount of resiliency built into the trial and error over all those years and the problem solved over all those years. So you're able to take advantage of that with RDMA across either Ethernet or InfiniBand. So how? So RDMA is built on what's called Q pairs, and this is a receive and a transmit pair, and basically they control the endpoints. They're how you get at that hardware engine. So a connection gets established between two nodes across the network. There's a registration process. This is super important for our persistent memory over fabric. So basically you're registering memory across the fabric. So a memory location or a field of memory on one machine is now available from another machine. Send and receive, those are two-sided messaging. Those probably don't fit except for maintenance kind of management messaging in persistent memory over fabric, but the read and the write RDMA are the one-sided, and I'll go into a little bit more details on them and show why they fit. So send receive, like I said, not super important. It's basically, like any network protocol, you set it up, you request data, you get the data, and it gets acknowledged. I'm not going to go into too much detail on this. One thing to keep in mind here on my chart, so here's the host system, here's the adapter. This is probably I stole it as an InfiniBand slide, so it says HCA, but that could be an RNIC as well on Ethernet. Here's the adapter on the other side, this vertical line, the host on this side, and there's the memory of the target we're talking about from a network perspective, or from a persistent memory over fabric perspective. So here's what the write looks like. Now remember, we're talking about memory, moving memory across the fabric for high availability. So in a situation where you're running an application that you have to know that data is always going to be available no matter what kind of failures occur. So you've got to make sure it's not in one box. All right, so what happens is you have registered this memory. So there's a memory region across the network that you're allowed to write to. You do a write. From that point on, from the moment you kick that off, the RNIC is taking care of it. So the data is moved, and you get a completion when it's done. As it was said earlier in the keynote, that you can do this, or they were testing this at under 2 microseconds. Keep in mind, that was done with technology 2 years ago. So that was a 56 gig InfiniBand and Gen 3 PCI bus. And here's the read. Same basic setup in the other direction. So you've registered, So you've registered the memory region. There's an RDMA read. It gets kicked off from then on by the adapter. When your data is in your memory, you get notified. You've read the memory across the network. And again, very, very low latency. So a couple of tweaks. I'm going to try to fill in those holes that Stephen left up in the top corner on the network interface that aren't covered or aren't solved yet. So there's an organization that handles RDMA, and they're set up a little bit differently than organizations nowadays. It's called the IBTA, and they handle the RDMA protocol. Nowadays, most of these standards you can look at while they're being developed, but that standard was set up so that unless you're a member, you can't find out what's going on there. So hypothetically, there may be some tweaks occurring to RDMA to fit persistent memory over fabric. And this hypothetically could be one. And this is, a flush operation. So basically what occurs is, I showed earlier, is you've got your writes, and now you've added a special command called flush. And this flush works with whatever mechanism exists on the target system, hopefully hardware at some point that's accessible from the PCI bus. And that then is acknowledged once the flush has occurred all the way through all the caches and you have persistency guaranteed. Then there's one kind of exception, or one thing that makes it a lot easier, and that's a non-posted write. And this is to get around the problem when you're writing a bunch of data that's going to be shared for whatever reason. Maybe you're going to update a pointer after you've written it, and you want to make sure that the flush has occurred before you update that pointer, so you don't get into a consistency problem. This might be, if you're using one of the models Paul showed where you're sharing some memory, you want to know that you have access to that memory, so it's a flag that's set. Or it might be a pointer, from some type of a record or a log. In any case, this is another slight hypothetical modification that could occur to RDMA to allow you to know that the flush has occurred and before your write. So if we look at the programming model, the SNIA programming model from a standard that is open, and you can look at the specs, you see, and it was talked about earlier, how that works from a high level, from the application level. So there's the map function, and the map function maps to the registration that already exists. The sync function, so you would then, your file system or whatever is storing locally. When it hits its flush, this is at the application level, that then gets transferred to a bunch of RDMA writes and a flush at the RDMA at the network level. Once that flush occurs all the way to persistency, you now basically deregister those pages. So basically RDMA protocol with some tweaks is able to map directly into the SNIA programming model. So now some platforms that exist today for trying this stuff out. So trying to be totally vendor neutral, I did steal a picture from one of my company's slides. This is actually a product we call Bluefield, and it's an SoC, so it's designed actually to be a storage standalone JBuff for NVMe over fabrics, but because it runs RDMA and it has 100 gigabit Ethernet and InfiniBand interfaces on it, and it has Gen 4 PCI interfaces on it, and it has DDR4 interfaces on it, and it supports hardware offloaded RDMA transactions, which I'll talk about in a second. It's a perfect platform for doing persistent memory targets. So it has an engine that's designed for NVMe over fabrics that allows you to do the protocol within the hardware, so there's no CPU interaction. And that can run at 8 million IOPS per second with 512 byte MTUs. So, and that mechanism would work perfectly with products that sit on the PCI bus with NVMe interfaces. And you can also use that to write into memory into DRAM or NVDIMMs. The latency is super, super low. So this is a round trip in and out of an NVMe device, how much extra latency is added. And it uses, basically zero CPU utilization. There's also other vendors that provide solutions similar to this. And it fits the requirements that Stephen laid out pretty well. So you have a control plane that is not involved in the data transfer, almost zero CPU utilization, and it's open source, right? It's ARM-based, so it's programmable by anybody that wants to grab software. You have multiple standard low latency I/O interfaces, so 100 gigabits, either InfiniBand or Ethernet. And it has multiple standardized interfaces for connecting the persistent memory, either through the DDR bus or the PCI bus. And it's a single ASIC, so low cost. That's all I had, but I think if we have time, all of us can take questions, Paul and myself and Steve.
Hi there. Well, anytime you talk about fabrics, the question of quality of service is going to come up. How has QoS been architected into these solution spaces?
Yeah, so you can architect that into either the adapters. Well, I can only speak to my company, but I think that it's a common feature in adapters to have QoS through the adapter, but you can also implement it on the fabric as well. And then if you're looking at comparing it to Gen Z or some of the new fabrics, what they're going to do is like Fibre Channel used to do, which is a total standalone fabric that's isolated. So you can approach, solve that in all three ways. But the beauty of doing this on Ethernet using the correct QoS is you have a unified, single, well-understood fabric, of course.
Okay.
Stephen, you want to jump in on any of these?
No,
Please
I
do.
think you answered that perfectly.
Okay.
So can you update us, what's the availability of RDMA on cloud vendors, with cloud vendors like AWS or any other cloud platform?
Yeah, you would have to ask those vendors. Sorry about that. I can tell you that quite a few of them have the capability in their networks. Whether they're supplying it to users or not, I think they are, but you really have to ask them.
Okay, so hopefully it'll come soon then.
I don't know. Do you know, Steve?
I think it's public knowledge that Azure are running. I mean, I'll agree with Rob. I mean, I think all these guys are using it internally. Whether they expose it to the consumers like us is really their choice, and you need to ask them about it.
One thing I can tell you is that there's SDKs available from multiple vendors that have the capabilities on the slide I showed earlier. We have one for Bluefield. Like most SoCs, right? You can get them as a motherboard. You can do whatever you want with.
So is there forcing for the multi-ports DDR? And the second question is, what software you are looking for, Stephen?
Stephen, you better come up on the software. What was the question on the DDR4?
Multi-ports.
Yeah, multiple ports. Well, at least our chip has multiple ports, yes.
So instead of DMA and Is there any other multiple ports for multiplexing CPU to access to the DDR4?
Sorry, I don't understand the question.
So the things that we can share the memory as a memory centralized system, and in that case, we can do the multiple exercise.
You mean across the fabric, can you share that memory?
Memory not only for the DMA engine, not limited by one engine, but it can multiple
Oh, yeah,
exercises.
you can have multiple
Yeah.
connections going in and out of it. Yeah, absolutely.
Yeah, I mean, I think if you go back to that diagram, right, there's nothing to stop you adding more NICs. One thing I'll say is even in this diagram alone, you have for want of a better word, shit ton of DMA engines, right? You got really high performance ones in those RDMA NICs. You've got every NVMe device I know of has a pretty high performance DMA engine. Most of them supports, well, some of them support scatter gather. So you can move data around pretty darn fast in a system like that, and then pump it out onto the fabric through products from Rob and many other companies. And then for the second question, I mean, I think one of the biggest things I think that would be interesting to look at, and there is some academic work in this space and maybe a little bit of industry work, is taking persistent memory aware file systems like the DAX-based file systems we have in Linux, like the DAX NTFS that we have in Windows, and extending that so it works across a fabric, really. And so today, one of the most obvious ways we have of doing that is using the RDMA replication library that Andy's team has done, where you could actually take a DAX file system locally and then hit a command and say, hey, do you mind copying this to 3 different places just so it's safe? And so we can do that today, but that's not really the same as being directly talking to the remote device, the remote persistence. You're talking to local persistence, and then you have a mechanism to back that up when you need. And I think there is definitely stuff happening there, but seeing that happen a little more would be great.
This is what Stephen's talking about, is actually implementing this.
Paul, you should come on.
You had the picture of the PCIe switch there, or can you go to that? I mean, I've been seeing this architecture for like a decade, it seems, where, disaggregation of the servers and everything. I mean, that's not it. Yeah, that. Or, I mean, is it more than 1% of servers doing this, or?
So I mean, this is the way storage data center servers are going right now as we transition from a SCSI world to an NVMe world. So the compute layer servers do not look like this, right? There's no reason for them to have that much storage. But certainly the data center customers and even now the storage OEMs, as they transition to NVMe in their product line, are building out systems that look like this. They have a CPU for the head node. They have network connectivity in the form of Ethernet or iSCSI or, heaven forbid, still fiber channel. And then they have a bunch of NVMe drives which have to be switch connected because you have 40 of them and they have 4 lanes, and 160 lanes of PCIe don't come out of an Intel processor.
Why are you bashing fiber channel? I mean, most
Because
of NVMe,
I love bashing fiber
over
channel.
80% of NVMe is all over fiber channel now. So
Yeah,
no
I just
one
like
likes to
bashing
mention
fiber
it.
channel. I even spelt it wrong in my slide, and nobody noticed.
It's sort of a broader answer to your question about, are people going to do this? As persistent memory becomes available and we start talking about being able to build pools of persistent memory in large-scale systems, I think you'll see the uptake. You don't see it now, of course, because they don't exist yet. But as they begin to exist, I think you will start to see it, provided that there are compelling use cases that say, I really want to be able to use remote persistent memory as a memory service like that. There's a little bit of a chicken and an egg going on here.
But as
you would
Paul
expect.
showed in his first few slides, there are use cases.
There are use cases, right? We're beginning to drive those. When it becomes available, yes.
I mean, they're disaggregating the compute and storage today using these kind of parts. So the next step, they'd love to disaggregate the compute and memory.
I think, Scott, I mean, to this point, people are definitely building block-based NVMe over Fabric servers like this now. I mean, we have multiple ODMs building that. They are not they are not natively being designed for persistent memory over fabrics. But I think one of the points I was trying to make is, as this persistent memory region feature of NVMe becomes more adopted, we can actually upgrade those block-based disaggregation targets into memory semantic disaggregation targets without changing anything inside the server from a hardware point of view. In fact, and very little from a software point of view as well.
And in fact, and I didn't go into it in too much detail, but hypothetically that standard, those changes to the standard for RDMA are designed to be very slight. So if you notice that flush command looks an awful lot like a write. You know, maybe a bit would change or something.
I wanted to put my Open Fabrics Alliance hat on for just a second here too. The question about software, Stephen raised this question, but there is this organization, the Open Fabrics Alliance, that is focused on software for networking for specific cases like this, and we are looking carefully at what it would take, for example, to run PMDK over a generic fabric, if you will. So there is a lot of work going on in that area. If you're interested, it's worth taking a look at what the Open Fabrics Alliance is doing in this area.
Other questions?
So the question was, can you go and buy NVMe drives with PMR today? Yes, come and talk to me. And I will pass you on to a vendor that may or may not be me to have more discussions.
I think we're done.
Thank you very much.
Thank you very much, everyone.